In this video, we're going to go through another application. This one is called the single source shortest path problem, the shortest path from a designated starting city to every other cities in the graph. So the actual printout is a table detailing your from and to, as well as distance between the two. So this is the shortest path. There might be other path that gives you a bigger number, but this one gives you the shortest path. Let's look at the approach. So there's a couple of initial representation of this approach. Essentially, it's just a queue problem. We're looking for the shortest path from city to city. We go for the fastest. Sometimes the more meaningful approach, and that is use the level order. Level order involves breadth first search, and breadth first search is queue, right? Queue-based approach. We're talking about priority queue here, not just the queue, because what is embedded in there is your minimum distance, your minimal distance or shortest path to the destination. There's this sense of prioritizations here. You don't want to just give it everything, but the minimum distance to and from. Everything else is the same. You have the outer loop as well as the inner loop. Inner loop calls for the iteration of your child vertices. Each vertex is linked to, and then setting up the flight. Notice that the creation of flight happens here, and then just keep using the flight along the way, even at the lower end when you enqueue this flight into it. When you create an initial flight and you just keep changing it, flight set is to change it. You'll have another flight set. This is a high level, and then this is a lower level, the parent vertex, and then iterating through all of the adjacent vertices. By you making these changes is the problem, because there's only one flight object. When you set something set from vertex on the outside, without even looking at it, you can see already that what gets enqueued in this priority queue will change, right? Depends on the inner loop here. So this is what the author refers to as the erroneous approach. So let's look at the correct approach. First of all, this is the priority queue and not a FIFO queue. We're talking about information that has the shortest path. We stop only when there's no more destination to visit. And just be careful of the use of reference-based priority, because reference means if you're setting something here already, you set it again and you try to enqueue it, information that you have set from before, even on and outside of the while loop would have been gone, because you're talking about reference to an object, indirect address to that object in memory space. Later on, when you change it, the previous reference to it also change as well. The incorrect path of the algorithms, making use of flight, changing it again, before on the outside of this while loop, the certain things have changed already. This is the inside of the while loop. Outside of the while loop, also has the same flight being used here. The correct approach is creating a new flight. Once you have a new information about this flight, when it gets down to this inner while loop, which is getting through all of its adjacent vertices, then you want to create a new flight object, embedding the new metadata associated with these adjacent vertices. One at a time, as in, because this is a while loop. Every single one of this newer path leading to the two vertices associated with this vertex would be a new flight object. And then you enqueue this thing. Later on, you can dequeue it, so on and so forth, and get it. So this is the right way to do it in the use graph. You see the use of new here inside this one, safe flight. We know that safe flight was used outside. This safe flight is also used multiple times. When you get to enqueuing a new object, this safe flight information is overwritten, so you don't just keep reusing the same thing, pulling out of this safe flight the same object that was changed before to protect the integrity of your code. The rest of the code here is just for printing out the information once the while loop is done, with the exception of the unreachable cities. Everything else will be printed as is, and there's going to be this header here. This completes a quick overview of your shortest path applications.